All right, folks. Is that okay if I just go over sort of all the topics? And then if you have particular questions, then we can do that as well. All right, so we're dealing with mirrors and lenses. Where's my pen? There it is. Let me just go over the types of images that are formed by each, and you'll need to know that. I'll sort of lay them out side by side. But this is like your ray diagrams will help you with this as well. So you also need to know how to draw the ray diagrams as well, because there'll be one or more questions. Just these are ray diagrams. Which of these are correct or incorrect? All right. So let's see. All right. So mirrors, and then you have lenses over here. If you have concave mirrors, there are three scenarios with these. Right? If your object is outside the focal point, it makes a real inverted image. I haven't said this before, but it's actually either smaller or the same size. Well, you can just say it's smaller. So a real inverted smaller image. And for lenses, the similar one would be the convex lens. Now both of these are converging. Right? And so even though they have different names, they're both converging devices. The concave mirror causes light rays to converge, and the convex lens also causes light rays to converge. And so they act very similarly. To have an object outside the focal point, it's going to produce a real inverted smaller image. All right. These are like the images that y'all made in lab, like of the light bulb with a little screw on it or whatever. Then you can also have at the focal point. In this case, you get no image at all. Similarly with the lens, if you're at the focal point, there's no image. And then inside the focal point, remember this is like a shaving mirror. Remember, put a shaving mirror up real close to your face, then you see a virtual upright smaller image. Excuse me, not smaller, bigger. All right, so this is like a shaving mirror. And then for the convex lens inside the focal point, you get the same thing, virtual, upright, bigger image. This is like a shaving mirror or a makeup mirror, or the purpose of it anyway, when you hold it up close to your face. This is like a magnifying glass. So y'all used a convex lens in lab to use it as a magnifying glass, and you could make the object look bigger. Virtual, upright, bigger. Virtual, upright, and bigger. And then you also have the convex mirror. So this is the second class of devices, and these are diverging mirrors or lenses. This is a convex mirror. And this is a concave lens. Looks like this. Both of these produce virtual, upright, and smaller images. In all cases, it doesn't matter where you put the object. They're always going to produce a virtual, upright, smaller image. This is like a security mirror, right, in a store. For both of these, also, these both have a negative focal length. So if you have a problem that has a concave lens or a convex mirror, you'll need to put the focal length as a negative value. Likewise, up here, we have positive focal lengths for both of these, the concave mirror and the convex lens. Remember, converging devices have a positive focal length. Diverging devices have a negative focal length. And then if you remember that, and then remember convex mirrors, concave lenses, these things are diverging, these are converging. So you sort of need to classify them in your mind as converging and diverging, because that's how they're similar. The convex and concave is just based on the shape. That's why it's called that, because they have shapes. Okay? Um, so you'll have a number of questions dealing with your ray diagrams. I'm not going to go through those here, but you should go back and look in your notes. If you don't have your notes, you can look online as well. There are some screencasts there. But you'll need to know how to draw those ray diagrams. A couple questions, just are these ray diagrams correct or incorrect? Okay? Y'all are good on that? That's 8 points or whatever. You'll have several questions on using the lens and or mirror equation. And on those, you need to be careful because you'll need to look for the sign of the focal length. So like 1 over f equals 1 over q plus 1 over p. So remember, you'll need to look for mirrors. I already wrote this once, but if it's a concave mirror, that's a positive focal length. If it's a convex mirror, it is a negative focal length. And then you also need to remember, sometimes I won't give the focal length, I'll give the radius of curvature. And that is, the focal length is 1/2 the radius of curvature. In fact, often that's the way I'll give it, as I'll say, the radius of curvature of this device, this mirror or lens, is blah. And then you need to take half of that to find the focal length. All right? It could be, actually it will be, that you'll have to solve a simple system of equations. All right, so we had a homework problem like this, and I'll direct you to that. But let me show you. I'm going to do it without numbers. Let's say that I know, I don't know, F, and I know M, and I want to know Q or P. All right, I have this 2 equations, and I have 2 unknowns, Q and P. You need to be able to solve for one of those. In order to do that, let's say I wanted to know let's do P. What is P? Then in order to find P, if I know the magnification, let's say the magnification is, I don't know, 2, and that the focal length is 1, just to give some numbers. If I wanted to find P in this case, I would solve this equation for Q, right? And I would say Q is equal to negative P times M. And then I would plug this in up here, and I would solve that now. Okay, so it's a system of equations. I don't usually do this on tests, but it's a fairly simple system of equations. And you have a homework problem almost identical to this. Okay, so just make sure that you're up on this. 1 over f equals 1 over negative p times m plus 1 over p. And then you would solve this. Okay? 1 over f is 1 equals, see what was m2? Negative 1 over 2p plus 1 over p. You can solve this a couple different ways. I'll find a common denominator of 2p. So 1 equals negative 1 over 2p plus 2 over 2p. This is just algebra here, but you would have 1 over 2p. And then solving that for p, cross multiply. 1 equals 2p, so p equals 1/2. Okay? That's about the problem with the most algebra would be something like that. I don't know if it's a lens or a mirror, but as I said, if you want more practice, there's some practice on the homework questions about this too. I forget, there were 1 or 2 questions like that. Several mirror or lens equation type problems. Watch out for the focal length. Watch out for the signs for various things. You also need to be careful when you're looking at problems that you remember those types of images that are formed. Like say, for example, if I gave you one of these and I said that your image formed by this mirror is upright and bigger, then you would know that this would be the type of mirror that you're using, right, from that information. Because there's no other mirror that produces an upright, bigger image. Right? None of these other mirrors produce an upright, bigger image. So in that case, you would know, 1, that my focal length is what, positive or negative? It's positive. These all have positive focal lengths. You would also know that your image distance is positive or negative. It's going to be negative. So that's another thing, is that our real and virtual images are given by our image distance. So real images. So that would be information that you would need to solve a problem, but not explicitly stated. But if you know the types of images that are formed by the mirrors and lenses, then you'll be able to determine what those things are. So if I know that's an upright, smaller image, or excuse me, is that what I said? Upright, smaller image? Yeah, if it's a convex mirror, if it's upright and smaller, it has to be a convex mirror. And if it's ever upright, it has to be a virtual image as well. So real images projected on a screen, they have a positive image distance. Virtual images cannot be projected on a screen. They have a negative image distance, and they are always upright. All right. Real images, on the other hand, are always inverted. When we're dealing with one lens or one mirror as a caveat, because if you have two lenses or mirrors, it's possible that the first one can flip it, and then the second one can flip it again. We'll get into that in just a moment. All right. Also, the magnification. Remember, we can find our magnification in a couple of different ways. I can say that it's HI over HO, the height of the image over the height of the object. And then I can also find it in this way, negative Q over P. Because virtual images are always upright, and because they have a negative image distance, that means if this Q value is negative, that means our magnification is going to be positive, because that have two negative signs. Okay, so that's why they're always upright, or that's mathematically how we describe them as always upright. Okay, two lens systems as well. You'll have, there's just one two lens system. That shouldn't be a big surprise. I think I told you in class. These are not much different from a one lens system. All right, I have focal lengths here. I have an object outside of the focal point, for example. My image would be, say, right here, and I can calculate what this distance is. This is Q1, P1, F1. Just from the lens equation, I can calculate Q1, and we can work through some problems like that if y'all need some help with that. And then I want to treat this image as the object. So this becomes the object for lens 2. And then it just becomes another lens problem. So I'm going to treat this distance as P2. So I would give you the separation between the lenses, and so then you would just subtract the image distance Q1 from that. So for example, if this was, I don't know, 10 centimeters, for example, and this was 30 centimeters, then P2 would equal 20 centimeters. And then you go about your business. So if this is F2, then we can calculate what is Q2. Right. As I said, we can work through some of these lens equation problems in a bit, but you need to be practicing them. If you haven't practiced them, well, if you haven't practiced them yet, that's not good. But just to make sure that you can deal with the algebra, because sometimes students just get hung up on fractions, and it's useful for you to just, refresh that. Okay. Don't forget your magnification. You also calculate your M1 is negative Q1 over P1, and M2 is negative Q2 over P2. And I'm pretty sure on that problem that I asked, what is the total magnification? And remember, to find the total magnification, you take the product of these two. So to find the total magnification, I just say M1 times M2. The product of those two. So for example, if the first image is, I don't know, a quarter the size of the object, and then the second image is half the size of image 2, then my total magnification will be 1/8. Let's see, I think, there are the atmospheric refraction and the mirages that you need to know about. So atmospheric refraction, remember, the sun goes down. This is the Earth, a very egg-shaped Earth. You're standing over here, and the sun is over here. As the sun is setting, The light rays can't reach you because it's below the horizon, but because of the atmosphere, those light rays bend around the Earth. And so you can see the sun even after it's set. And that's called atmospheric refraction. It allows us to see the sun even after it's set. And then there's also the mirage. So if I see something, I don't know, a tree or whatever, if there is hot air on the ground, as there is on hot days, light from this object will go towards the ground and then bend up and come back up to your eye. And that's going to look like it's appearing from below where the image is. That's a mirage. It looks like reflection, but it's caused by refraction. There's warm air that bends the light. I think y'all know this, but let me just remind you, for flat mirrors, we had a couple of rules, and that is that the magnification is equal to +1. You never look bigger or smaller in a mirror, right? In a flat mirror, you always look the same size. And then we also know that P is equal to -Q. And that's just to say that if I have a mirror here, this distance, P, is the same distance as the distance to my image here. That's always the case. We had a series of problems as well where if you have an object here, your image is always directly opposite. And it doesn't matter where you're observing that from. It's always going to be the same. Right? It's always directly opposite the object. I think that's it. Are those all the topics? Missing anything? You need to know the different kinds of lenses as well. Okay, we did go over that. The different kinds of lenses. I've already shown you the convex and concave, but also just be aware that convex plano lenses exist. These are plano-convex. They're planar on one side, convex shaped on the other, and then also plano-concave, which looks like this. They're concave on one side and planar on the other. I showed you a picture of a meniscus lens. There are actually two different kinds of meniscus, but don't worry about the meniscus. That's just sort of. I don't think they make a convex concave. I don't know what purpose it would serve, because one would cause the light to diverge, and then the other would just do the opposite. I've never seen one. They might exist. I'm not saying they don't, but I've never seen one. All right. Do they exist? Have you seen one? One was in the book? Okay, convex concave. No, yeah, I guess. Yeah, it looks like that. Convex concave. Okay, just remember your shapes. Okay, convex looks like a belly. Concave looks like a cave. Right? Okay, sorry, Blake. No, I did forget that, didn't I? So spherical. There are two. No. Let me address it though, Alex. No, just know what they look like. Be able to identify them. Anna Catherine? Yeah, I'll come back to that question, okay? Same. This one right here? This is called atmospheric refraction. And remember, it's just the sun. You can see the sun even after it's physically below the horizon because the light rays bend around the surface of the Earth. Okay? Aberrations. That was one thing I was missing. There are two types of aberrations, spherical and chromatic. You need to know what causes them, what effect they have, and what fixes them. Right. So spherical aberrations. What's that? 135, I think. Oh, 259. Spherical aberrations, these are lenses and mirrors, right? And the problem is that light rays coming in focus at different points from different parts of the lens. All right. They also occur in mirrors. They just focus at different points. So you get a fuzzy image. The easiest way to deal with this is just to put an aperture right there. Right. We did talk about how telescopes actually use parabolic mirrors. The easiest way to deal with this is to use an aperture, and that's sort of the most common way. The human eye uses an aperture. That's the pupil. Cameras all have apertures inside of them that block the light from the outer parts of the lens. The other is chromatic aberration. By the way, this is both lenses and mirrors. Chromatic aberration is only lenses because it requires the refraction of light. Chromatic aberration. Chromatic aberration is only lenses because it requires refraction, and mirrors don't refract light, they only reflect. So chromatic aberration occurs because the index of refraction is dependent upon wavelength, like that. All right, so on this end, what's this, the long wavelength? This is red, this is blue. All right, so our red light has a high index of refraction, so it's going to bend a lot. And the blue light has a low index of refraction, so it's not going to bend as much. So it'll look like that. All right, so your red image and your blue image appears separately at different focal points. It's called chromatic aberration. The only way to deal with this is you can set up a system of lenses. So you would put additional lenses in the path of the light, and that would mitigate some of the chromatic aberration. I think you can also put some sort of filter on the lens, which will help remove that. But it's sort of specific to your, yeah. No, the diffraction grading? No. No. Mm-mm. No. Oh, no. I got that backwards, didn't I? Yeah, I'm sorry. Don't worry about which color refracts more. Just different wavelengths refract different amounts. Yeah, I got them backwards. I'm sorry. So this should have been red, and this should have been blue. Thank you, Michaela. And it would switch the lines here, but don't sweat that. You probably don't have red and blue pens anyway, do you? Okay. All right. Any particular problems that y'all want to address? That's the test, basically. That's everything that we've done in this chapter. Yeah. I haven't gone through the ray diagrams, but I did go through the different mirrors. I'll go through them quickly. Like, this is what you mean? What produces what? Yeah, sure. We'll go through a couple of those. Any other questions right now? Okay, we'll come back. So think about what you have. I did tell the class that you will have several ray diagrams, or a couple of ray diagrams, I think, where you have to pick out which one is correct or not. Let's do the harder ones, okay? I think the easier ones are, well, they're easier, like the convex outside of the focal point, and then the concave outside of the focal point. Remember, those produce real images, real, inverted, smaller images. Well, let's do some of those that are a little more difficult. Like, let's do a convex mirror. Here's the focal point. There's my optical axis, and there's my object. Right? I can draw my rays. The first one goes parallel to the axis. Right? And this is a diverging mirror, so it's going to cause the light to diverge in this direction such that if you traced it back, it would go through the focal point. So remember that first rule is parallel to the axis through the focal point. Parallel to the axis through the focal point. So that's rule number one. It looks a little bit different than a concave mirror did, but it's still going through the focal point, or at least this virtual ray is going through the focal point. The next one is through the focal point and then parallel to the axis. You'll draw a ray that will come up like this, such that if you traced it forward, it would go through the focal point. And then it would come back parallel to the axis. All right? Now these rays are diverging, so I need to trace them back. And so I know my image is going to be right here, which jives with what we know about convex mirrors. that a convex mirror produces an upright, virtual, smaller image. A security mirror, right? Security mirror always produces a virtual, upright, smaller image. And remember, upright images are always what? Real or virtual? They're always virtual. Alex? No, you're not going to have to draw it. I'll give you a picture of something and ask you, is this correct or not? No, yeah, I'll have several rays drawn, and you have to say, are these correct? These rays correctly drawn. It will help you to know. I'll show you where the image is from the rays, yeah. No, I'll show you. All that will be done, but some of them will be done incorrectly. It will help you to know what type of mirror produces what type of image, because like if I show you a convex mirror with a big old image, you know that's not right, right? Or if I show you a convex mirror with a real image, that's not right. Does that answer your question? Right. No, I think I've had it where, like I have a single mirror. I have four. I show you four scenarios. All right, so you'll get the test tomorrow. There'll be two questions, and each of them will have four scenarios with four different mirrors. They'll all be like a convex or concave mirror, and similarly with a convex or concave lens. And each of them will have three rays drawn on them, and one of them will be correct, and all the others will be wrong. All right, is that clear? The correct set of rays. Right. Whereas just a single ray, that's right. Yeah, not like that. Is that clear? That's the first two questions. The first page, really. I think it's the first page. All right. I can go photocopy it. Okay. Okay. All right. So that's and then let's see. There are some other rays we can draw. I can also draw it to the center of the mirror. I feel like I'm missing one. Center of the mirror like this. I'm gonna fudge it just a little bit because I don't have a ruler. Uh, oh, and then through the center of curvature as well. I can draw one that goes through the center of curvature. Center of curvature is back here. You draw a ray that comes up such that if you traced it forward, it would go through the center of curvature, and then it reflects back on itself. Yeah, with these, you can watch me do it all day, but you really got to put your pen to the paper and okay. No, not this type. No, they're a little bit different. But I just explained to you what they were, so that should be okay, right? Sam? That's right. The focal point is one half the center of curvature, or the center, as you said, is twice the focal point, like the focal length. Right? On itself, right. hmm Right. That's right, yeah. So this isn't drawn to scale really, but these two angles should be the same. That's true for all of them, right? I mean, that's true for this one right here. It's true for all of these. But it's particularly easy to draw that green one. All right. So I think really, like y'all really you have to sort of look at those and maybe even go through them once, just drawing out the rays. It's 8 points on the test. Actually, more than 8 points, like 9 points. It's worthwhile, worth your while. All right. Um, Not that hard really. It's like yeah, nothing funky. Just, all right. That means there are no virtual objects. Do you know what I mean by that? Okay. Okay. What other questions we have, Michaela? No, she was just asking. For two lens systems, you can have a virtual object, That's where the object is on the wrong side of the lens, where you have a negative P. Y'all had that in lab when your lenses really close together and your first image from your first lens was way over here, and you have to take a negative P. I was just telling you that's not the case for the test. You will have a two-lens system, but it'll be more like what we did in class. No negative P, right? That's a little nicer. Correct. The image distance for the second lens will not be negative. It'll be a positive image distance, which is more what I drew in this little example that we did up here. Or I didn't do an example with numbers. I can do one is more like this example, which is easier, I think. You have your object, your first image becomes the object for the second lens, and then you find your second image. For each case, you find your magnification, and then you take the product of those magnifications. X prime. Oh, yeah. Gosh, that was a long time ago. Yeah, no X prime. That was an old exam, wasn't it? Did you? Oh, yeah. That was for like a microscope, I think, right? Or yeah, a compound microscope. Okay. All right. What else, guys? You okay with me not working through the numbers? I can. Okay. A bunch. Every test has an example like this. What else, guys? Okay. Hmm. No virtual object. Mm-hmm. Lens 2. You're always going to have a real object for lens 1, right? Because you just have this object over here. But it'll look like this. It'll look like this. If it doesn't, you have a mistake somewhere. Okay. Trying to think what else. That's all the topics. Yeah, Anna Catherine? Aberrations? Yeah. Right. Yeah, you can also add a system of lenses, but the simplest and the easiest way is to add an aperture. Right, to add a diverging lens prior to it. Or just add another lens. That's not what? That's not there. Really? You'll what? Okay, write it down, yes. Is that clear? To get rid of chromatic aberrations, you can add a lens prior to the offending lens, and it won't get rid of it completely, but it can mitigate it. Oh yeah, let's go over the eye. All right, so we had a couple questions about the eye and the camera, and they're different in a couple ways. One way, really. For an eye, the image distance is fixed, right? Your image distance is always this distance. This is always Q, and so that's fixed. What changes is the focal length. So the focal length is variable because you have those muscles, they can squeeze the lens and make it fatter in the middle, shortening the focal length. Now, if you're looking at something really far away, the light rays are coming in parallel. So this is an object with P equal to infinity, very, very far away. And in that case, the focal point is the same as the image distance. So in this case, F is equal to Q. The focal point is on the retina. That's where your image is going to form. But if I'm looking at something that's nearby, say I'm looking at something right here, then my focal point is going to get shorter. And you can see that by drawing the ray diagram parallel to the axis through the focal point. through the focal point, parallel to the axis. And so there, my focal length is less than the image distance. The maximum your focal length will ever be will be what? No, not 20. You're thinking near point, I think. What? Right. The maximum is Q, right? Because you can only look at something infinitely far away or something, 10 centimeters from your face. That's your near point. Right, so the maximum F is Q, which of course is the diameter of your eyeball. All right. Now cameras are a little bit different. Not quite as clever. Because instead of changing the focal length, you change the image distance. So for a camera, the focal length is fixed. So my focal length is here. So if I'm looking at something far away, where the light rays come in here, I move the film right here so that the light rays will focus on the film. But if I'm looking at something nearby, like right here, my image is going to form back here. So for this case, right, because parallel to the axis, through the focal point, parallel to the axis. This is my image. And so in this case, I'll move my film back to where the image is. So with a camera, you adjust the focal point, or excuse me, you adjust the image distance. For an eye, for your eye, you adjust your focal length. That's pretty clever, I think, to change the focal length. No other instrument works that way. This is going to go online too, guys. I mean, you're welcome to take pictures. But it'll go online as well. All right. What else, guys? Any particular questions you want me to work through, like old exams or whatever? Michaela? No, we didn't really talk about that. Just know that that's what you, yeah. Any questions? Any topics that are bugging you? Okay, the camera. On which one? The top one or the bottom one? Okay, the focal length doesn't change. So your focal point is always right here. All right, and if you're looking at something really far away, I put my film at the focal point. If I'm looking at something really close, my image is formed behind the focal point. So if I'm looking at this image right here, this object right here, its image forms behind the focal point. And so I have to take my film from here and move it back to here. Yeah, your ray diagrams will show you that. Let me redraw it over here where it's new. So if I have an object that's close, the light rays aren't parallel. So I have a light ray that'll come in here and go through the focal point, and then I have a light ray that goes through the focal point and parallel to the axis. So you see, here was my focal point right here, and then this is my image distance, Q. So if I'm looking at something up close, my image is behind the focal point on the other side. That's why for your eye, when you look at something close, those muscles squeeze down that lens and make it fat in the middle so that its focal length decreases. You have to draw two rays. That's right, yeah. So you always have to have two or more rays. And where they cross is where the image is. I think, like, knowing those ray diagrams, you don't want to spend too much time on it, but it'll help you in a lot of different realms because it'll help you to remember where the images form and what types of images form. Yeah. All right. All right. What else? Now feel comfortable? Comfortable? I was about to say that it's not a difficult test, but I don't want to say that because usually that means it is. But it's just chapter 7, so there's only so much you can ask about chapter 7. Yeah, Michaela? Right. So on the eye here, the red rays show that something's very, very far away. Because when something's far away, the rays are parallel. Right? Like rays from the sun are parallel. And they focus at the focal point. And so in that case, the eye adjusts, the lens adjusts to put the focal point back here. But if you're looking at something nearby, like this, your finger or whatever, the focal point comes up here to cause the image to form at the retina. Yeah. I mean, I could draw the rays. Actually, no. Could I draw them differently? Can you repeat your question? Yeah, anything that's far away, light rays when they reach you are parallel. Right. That's right. That's right. All right. I don't think so. I try to make it pretty straightforward, but the only thing that you might not have seen on previous tests are that system of equations, right? That's in the homework. That shouldn't be a big surprise. I try to go through and pick out at least a couple of homework problems. I mean, all the problems are similar to homework, but you might see some that are verbatim too. Not the same numbers, of course. But knowing those types of images will help you. If something's virtual, it's upright. If something's smaller and virtual, it's a convex mirror or a concave lens. That kind of thing will help you a lot. There are several problems where that comes into play, where there are things that are not stated in the problem. This shouldn't surprise you because the old test questions are that way too. But things that are not stated explicitly, like, oh, this has a negative focal length, or oh, this has a negative image distance, or whatever, where you can figure that out. So you'll need to read those little clues a lot. Read those clues carefully in order to determine that unknown information, which is really known, right? It's just hidden. Michaela? Uh-huh. Sure. Right. So for lenses, you have two focal points, right? You have a focal point over here and a focal point over here because you're bringing two curved surfaces together. Same for concave lenses, focal point, focal point. For mirrors, you only have one focal point, here or here. All right. What do you mean? No, because with the eye, those focal points change. Right. Okay. We can talk about it. Why don't you say after? Let's see if there are any other questions. Anything else, guys? You feel okay? Yeah? All right. It's your last test. Woo. Until the final. And whatever other umpteen tests you have this week. Okay? I'll see you tomorrow. Have a great day.